Hi, I'm Anil Kag. I'll be presenting our ICLR work on scaffolding a student to instill knowledge. Let us look at the paradigm of a teacher distilling its knowledge onto a student network. The standard distillation procedure gives equal importance to both the inputs panda, which is an easy input, versus a bear, which is a hard input. Although the student is a very tiny network and is not capable of learning hard instances like the bear image. That is, the distillation method focuses equally on the easy and the hard examples. To address this issue, we propose to provide additional help during training via the guide signal. The teacher explicitly says that the student should learn the panda example because it's easy, but it can disregard the bear example if it cannot learn this because it seems that the bear is hard for the student. This guide signal is what we call a scaffold or the help. In this case, the teacher provides extra help on the hard examples. Concretely, the standard knowledge distillation procedure consists of a teacher T and a student S. An input X is forwarded through both these networks. This results in the teacher and student logics, which are softened using a temperature scaling and converted into a probability distribution. Finally, a distributional loss such as a Kale divergence loss is computed using this equation. In our proposed method, DiSK, that is distilling scaffolded knowledge, in addition to the student and the teacher networks, we incorporate a helper function G. Similar to KG, an input goes through both these networks, which is converted into temperature softened probabilities. In addition, the teacher and student outputs are forwarded to the helper function G, which results in this scaffolded signal. Finally, this scaffolded signal is added to the student distribution while computing the Kale divergence loss. An extra budget term is added to avoid the trivial solution, that is, help on all the examples. Note that G is computationally cheap as it's a small neural network and is used only during training. Once the student is trained, at the inference time, only the student network is used. Let us visualize this using a one-dimensional example. Let us restrict ourselves with a teacher with two interval function class and a student to be a one interval function class. Consider the following data distribution of the red and the blue regions on the line segment. A teacher easily learns decision boundary with two intervals and achieves 100% accuracy, while a student with only one interval function class faces difficulty in learning this task and can get stuck in the following three minimas. One has 87% accuracy, the other one has 83% accuracy, while the last one achieves 67% accuracy. If we were to learn a student using a knowledge distillation procedure, it can get stuck in the following three minimas, which is 87, 83, and 67% accuracy minimas. While in contrast, if you were to learn this thing via DiSK, it seems to be eliminating the two of the other spurious minimas and lands us into the correct minima, which is the 87% accuracy minima. We can run these two procedures 100 times and record the frequency of each minima in various methods. This table shows that this consistently hits the correct minima most of the time. Empirically, as compared to knowledge distillation, DiSK results in up to 2.5% accuracy on C power 100. In both the scenarios where the student is a very tiny network as compared to the teacher versus where the student is a similar capacity network as the teacher. While on the ImageNet 1K, it yields more than 1% increase in accuracy for both convolutional and vision transformer architectures. To summarize, DiSK scaffolds hard-to-learn inputs for the student by exploiting teacher. It smoothens the student's loss function, often eliminating suboptimal local minima. It yields large and consistent accuracy gains over the vanilla KD for CNN as well as vision transformer architectures. And it can be applied in conjunction with other distillation procedures such as feature matching. Thank you for listening to the talk. Please visit our poster for more details and check out our implementation at the following GitHub repository.